the start of my editing there. So, okay, welcome to 2800. I'm Michael Hipfner. You can just call me Michael or whichever is easiest. I'm not too particular. We have two TAs. So Rashmi, I think, is going to show up in class on Wednesday. They're studying for their qualifying exam for their PhD program, so they're occupied today. And then Michael Barkdull took the class last year, and he'll be the TA in addition to that. I'll talk a little bit more. So office hours, I'll send out a Google or Doodle poll, whichever one makes the most sense, and find times that work for the most people. I tend to do my office hours on Zoom so that you don't have to necessarily travel to campus, but we can absolutely meet in person outside of those times. That just allows me to also record the office hours, and I've got a tablet. You'll see I'm very into these technology tools. So I'll record it so you can draw, and I can kind of walk through homework problems, and I'll go step by step. And then, so then the TAs, if you want one-on-one in-person help, the TAs are going to be the best option. They'll have availability, so you can build a good rapport there. A YouTube channel, this is where all the things are posted. Now, I have some videos that are on the YouTube channel that are publicly available, but most of the lectures that I'm doing now are all, I think it's called unlisted. So if you have the link, you can watch them, and I'm going to share all the links that are more data than you possibly could need. Course description, that's the same, just copied and pasted. The textbook, I forgot to bring the textbook, but it's listed here in the syllabus. I've got a couple of links here. I don't care if you get the 3rd edition or the 4th edition, right? It's not going to be critical that you have the same edition, just that you have a resource to rely on, particularly for data tables. Right? There's going to be a lot of material properties that you'll have to have access to. Now, potentially, your thermodynamics book may have all of that information as well, but I do recommend trying to find these. I would recommend trying to find them as cheap as possible so you don't have to necessarily break the bank. Course objectives, these are written in terms of, I guess, what they recommend for us educators in terms of tasks that you should be able to perform. For example, utilize vapor-liquid equilibrium principles to design steady-state unit operations that involve phase changes. Right? So by the end of the class, you'll be able to do that. So that's a flash separator, for example. So please read through those. For the grade in the class, it's broken up into a lot of different things. I think it's helpful, particularly for relatively early in the chemical engineering discipline, to have lots of reference points, right, to kind of make sure we're all staying on track. So homework is designed to be enough that you do it, but not enough that you have to stress out about it or that I have to worry about people begging for extra homework grades. And I'll talk a little bit more about that, but actually, since I'm here, I give out the solutions before the homework is due. Right? So the grading on the homework is going to be sort of what I like to consider a check, check plus, check minus system. Right? So if you do the homework, even if you don't get it 100% right, you're still going to get 100 points on the homework. Right? So if you try all the problems, you'll get the homework grade. Right? That's all I require. So the main thing is that because I'm posting the solutions, I'm offloading that homework challenge of did I do this correctly? Right? Do I understand the material? I'm offloading that onto all of you. Right? So use the solutions responsibly. If you don't use the solutions responsibly, well, it's only 10% of the grade, and it's not going to make or break the decision of what your final outcome is. The quizzes and the exams are going to determine that. Right? So the homework is there as a resource, as a tool. They are types of problems that I've very carefully written myself that I think test key concepts that you should know how to be able to do in order to advance in this class. Does that make sense? So I don't want to rewrite very careful and very cleverly designed ones. Because I find that a lot of the textbook problems that you find in the back of the books, they're just sort of grinded out type problems. Right? A lot of algebra involved, not necessarily testing a lot of concepts. Okay, so quizzes. Every day on Friday that we don't have an exam, there is a quiz. How the quiz works is I'm going to have a Google form that I will sort of send a link out the day before. You show up, you have to open up that form, and then I'm going to display the questions on the screen. Then you answer them in the first about 10 minutes of class. If you miss the first 10 minutes of class, you're out of luck, right? So I drop the two lowest quizzes. So you don't have to ask me if, hey, I'm going to be out of town on Friday. Can I make up the quiz? That's fine. Once you got 2 of those to burn through, they're really just there as a checkpoint. The problems should be relatively straightforward, and they're going to be pertaining to the content that we covered in class that week, right? So I think there's about 9 of those quizzes or something like that. All right, we have 3 midterm exams, pretty standard exams, right? The final exam is broken into 3 sections. So the first section here, midterm exam 1, is going to be focused on general engineering principles, so like units, unit conversions, that kind of stuff, and also mass balances, right? X amount of component 1 goes to a system, X amount of the component comes out of the system, what's the change in composition? That's going to be the emphasis of what we're doing for the first part. The second one will be focused on phase changes and thermodynamics. The third one is going to be focused on energy balances. The final exam is going to have 4 parts. One that focuses on exam 1, one that focuses on exam 2, one that focuses on exam 3, and then a final portion that is sort of a grab bag of assorted questions. So in that aspect, let me go down to here. So if you do, not ideally, I'm not going to say poorly, less well than you wanted to do on exam 1, 2, or 3, you can, if you do well on the final, I will average, right? If you do better on the final, I'll average your final score of that section with your exam score for 1, 2, and 3. Does that make sense? So exam 4, part 4, everyone's got to take. But if you did, non-ideally on exam 1 and you ace section 1 of the final, I will average those together, right? So you'll get sort of a double counted bonus on the final, right? My objective here is not to penalize people and try and find a reason to fail everyone. My objective is to award people and try and find reasons to pass everyone, right? I care about you getting to the finish line by the end of the semester, and I think this is a good strategy to do so. Question?
So, let's say we do the opposite, we do really bad on the first section.
Does not hurt you. Yeah. But you do have to take the final. It's not like if you get 100 on exam 1. Yeah, was that?
It doesn't hurt us, you say?
It does not hurt you, yeah.
So how does that?
So it doesn't hurt your first exam, but it hurts your final score. Yeah. Yeah, so it'll hurt your final score, but it won't, so you don't get to choose which of those 2 count as part of that. So you still have to take the final, because then you would have forgotten stuff that you did know, which goes against the objective, right? Because I want you to know it by the end of the semester. And then for the exam itself, you get 1 page front and back for every single exam, and then on the final you get your 3 pages front and back, and then you can squeeze in. I'm sure you're not filling out every square inch of space, so you'll get 3 pages front and back for your final. So that's 1, 2, 3 for each of the 3 midterms. One piece of advice, I'll be talking a little bit more about this because this is, I would say this is an insanely difficult class, but it's difficult in a way that no one is used to yet. And I'll go into more detail there. So you can only use what I would call sort of a normal calculator, right? So nothing that connects to the internet. So for me, this is my TI-89 from, I don't know. 1989? Close. Probably like 2004 or something like that I've been using. So I'll tell you a quick story. I was in my sophomore year. I did my undergraduate at the University of Utah, and then I did my grad work at University of Michigan, and I came back to be a professor here. I did my PhD with Scott Fogler, whose book you're probably going to use next year in your reactor design class. So I was sitting in thermodynamics as a sophomore, and Jeff Silcox was the professor who just retired this year. Okay, and I had derived an equation. I was like, this is the equation. I was like, gosh, I really, really don't want to solve this equation. And I realized, wait, this isn't a math class. This is an engineering class. So then I just typed it into my calculator, and I let it do either the linear algebra or the nonlinear algebra, or the systems of equations, whatever it takes. So I recommend, now this is ridiculous because it still costs like $100 or $120 that it used to like a million years ago. But I'll tell you what, in terms of an investment of your future, don't do algebra on an exam ever again. I highly recommend getting a calculator that you can do algebra, and it'll save you an immense amount of time. Right? So for me, I just click solve, I type in the equation, comma x, enter, and it solves it. Right? It eliminates a source of error. This is not a math class. This is an engineering class. Right? This is the first sort of what I would consider real engineering class that we have in our curriculum. Right? Yes, question.
So I have one of those calculators, and I didn't know if you do algebra.
Oh yeah.
Do you like tutorials, or is that on
No, I'm not going to. But if you have it, so you hit, there's a button here that says solve. You hit solve.
Where is the solve button?
F3. Do you have a TI-89?
My TI-84. No, 89 is way more advanced than the
89 is solid. That's all I'm going to say, guys. 89 is solid.
CAS, is that like allowed?
Oh, what's that?
The really fancy one. I don't remember what it's called.
If it doesn't connect to the internet, that's fine.
I think it can, but it doesn't.
If you,
plug it in.
I mean, even if you can connect your calculator to the internet, boy, you're not going to have the time to use those features. But anyway, if you have a TI-89, you click solve, you type in your equation. There's even an X, Y, and Z buttons here. Type it in, equals whatever, and then comma X, and then hit enter, okay? So this is going to be a strategy to make you way more efficient on your homework. So on your homework, you can just use Wolfram Alpha or whatever the case is. But on the exams, this was my silver bullet when it came to passing engineering classes.
I have another question.
Yes?
What if you forget your calculator multiple times?
Tough luck. Sometimes, if you're very nice, I will have this and you can use it, right? But like first come, first serve, right? So sometimes if it's chronic, I have some spare calculators that I'll try and throw in. But the first person to request it will maybe get to use this one. But then the other ones may be substantially less capable pieces of equipment. Okay, any other questions? All right. So let's see. Okay, this is an important one down here, regrading requests. See if I can highlight it. Now for the homework, I'm usually not super concerned for the regrade request, but on the exams, if you think that I was unduly harsh, oftentimes I don't propagate the uncertainty, right? So I try and grade on method, right? So did you get the right equations? Did you set them up correctly? Did you manipulate them in the right way? Then I try and make it so that the final answer is only worth a handful of points, right? And I generally don't propagate numbers or uncertainty, right? And so I kind of offload that responsibility back onto you. And so if you get the grade back and you're like, wait a second, I thought I got this almost all the way right and I made one small mistake, that's what the purpose of the regrade requests are. So when I hand the exams back, you get 1 week from that day to hand back to me your exam and a written document that basically resolves the problem and outlines what the one mistake you made is, or 2 mistakes or 3 mistakes, depending on how lucky you want to be, right? And say, hey, look, this is what I did. This is the one mistake that I did wrong. I'll take a look at it, and if I think that, yeah, you're right, you did actually get most of the understanding right, and you made one silly mistake over here, right? You used 0.2 instead of 2 point for something like that, right? So I don't necessarily go through the hassle of doing that because it's a relatively large class, and so that would be a lot of time in the grading. I'd much rather get the grades back to you. So this is the strategy here. So reread this and make sure that when you hand in your regrade request, that document is comprehensive. You've shown that you've gone through the solutions, that you've worked through it, right? This is your voice in the room when I'm reconsidering grading of the exams. Okay. Academic misconduct, I think we're all pretty clear of what constitutes misconduct. Don't cheat, right? Don't misrepresent. Do work in groups. Absolutely work in groups. And not all groups are created equal. Not all people who are good at the class content are good at teaching the class content, right? So you may find yourself in a group where someone like, oh yeah, this makes sense. Oh yeah, this makes sense. And you say, how do I do this step, right? And they just tell you how to do it, right? But they don't tell you why they did it that way. So make sure that if you're working in a group, right, and there's differing skill levels of people in the group, try and gravitate towards individuals that will explain why they're making the decisions that they're making, not just what they're doing, right? Because just because you get all of the homework right, matches the solutions perfectly, doesn't mean that you necessarily understand the solutions, okay? So the best people in the class may not be the best at explaining the content in the class. But just make sure that when you hand it in, it's your own work and you understand it, right? The homework is there to help you understand the content and to do well on the exams. If you do well on the exams, then I feel good letting you out into the world saying that you know how to do mass and energy balances. Dun, 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 dun. Academic conduct will not be tolerated. Misconduct. Okay, grading cutoff. These are the worst case scenarios. They're almost always lowered, so don't stress out about that. Right? I just put a standard there so that I can lower it down to what I think is an appropriate level. Okay, so this is an important one here. Particularly, many of you may be in your, first or second year at the University of Utah. I believe it's still called the CDS, the Center for Disability Services. If you have any concerns, anxieties, learning disabilities that prevent you from showing your true understanding of the course content, please absolutely reach out to the CDS, right? We always have a handful of students every single year that use their services. No one will judge you, right? At least I can't count for every student in the classroom, but all of the academic staff at the University of Utah, you will not be treated any differently. The goal of all of this is to get you to be competent chemical engineers, right? The goal of this is not to get you to be competent chemical engineers in 50 minutes, right? So don't be anxious to do this. If you need the assistance, please do reach out, and there's no consequence or harm on us or anything like that. These are some more university mandated or suggested information, so be nice to everyone, please. And then the syllabus. So for this here, this should be a copy. I'm going to switch over to our electronic syllabus. So this here, and I wanted to show you all this on the Canvas page, but it's the first day of the semester in the new year, so apparently UIT did something that messed up Canvas, so I can't show you. But if you can get on the Canvas page, all of this is on the main page with links, okay? And I'll go through that, and hopefully that's not confusing. So this is a Google, what do you call it? Sheet? Yeah, Google Sheet that has our whole syllabus. It's exactly the same copy as what we have in the PDF form. And so these links right here, I've made them all red. So those are last year's links. So you'll get to see me with my pandemic haircut or lack of haircut. I'll update these as we go. So if there's any sort of problem with the video recording or audio recording, which will happen, I'll just keep up last year's, or I'll substitute in whichever one, if we're ahead of schedule or behind schedule, that best matches that particular one. So this is where you can find the links for the actual in-class recordings. This is the content in an ideal world that we will be covering in those times. And then over here, there's a series of videos that are kind of independent. And so these are ones that either I made in the, darker yellow, or by a service called Learn Chem E channel. That's by the University of Colorado. I don't particularly love Learn Chem E, right? But I never listen to it on 1x speed. I always listen to it on like 1.5 speed or something like that, okay? So these are all concepts that are sort of independent little modules that'll help you understand what we're going to kind of be going over in that class. So these are good resources. If you find that you're falling behind in class, right, and you're not quite sure of the content, you can either go back and rewatch some of these and take notes, or counterintuitively, by falling behind, start to move forward, right? Watch last year's lecture before the class. Watch these videos before the class. Then you'll be prepared to ask questions, and you'll get more utility out of the individual lecture itself. So I have the midterms marked out. I've got the days off marked out. One thing that I do is the week before the first midterm, I give everyone the midterm from last year in class to take, right? So you get the real anxiety of the real exam from the previous year, and it's a good sort of benchmark to say, huh, maybe I don't know this content as well as I did, right? So what I'm looking to accomplish here is, in many ways, proficiency of understanding, right? So you got to really know the content to be able to crank out the problems, right? So if you knew exactly how to solve the problems and to physically write them out, a 50-minute exam should take you 5 to 10 minutes, right? But a lot of that time is like, okay, what should I do? What should I start with? But if you saw the solutions, you just had to transcribe them, basically, it would only take a handful of minutes to solve the exams, okay? So they're not intended to be massively involved algebra, but it's more so like, if you know the right starting point, they'll fall into place pretty quickly. Yes?
Will we have access to the other previous year's exams to study for outside of class?
So I'll give you every one of the previous year's exams as a study guide. But I only go 1 year back, usually. Yes?
Unrelated to the exams, but like for the book sections, are you expecting us to read that like prior or after class, or is that kind of stuff that we can read if we don't fully understand what was being taught in class?
See, this is where I get into a bind. I was never a particularly good student. I didn't necessarily read all the book chapters. Would I be better off if I did? Yes, probably. So that's up into every individual's best practice. I think it'd be a good idea to read up on these. I, in my personal career, would refer to them when I didn't know what was going on.
So you'll teach us everything we need to know.
I think so. I hope so. That's the plan. I'll teach you everything that I think is important to know in the class, but I will skip over some details that the book will fill in more rigorously. But the book is a good study guide for example problems because they'll walk through things on how to solve it. So for me, for example, when I'm not sure how to do a particular calculation, I'll go to the book and I'll follow along with the examples, right? So us as teachers are not, omniscient beings, right? So we still have to relearn all of our material. And so the textbooks are useful for us. So I'll do more textbook reading almost when I'm teaching the class than when I'm taking a class. But it depends on the rigor and difficulty. And everyone studies a little bit differently. So some people, I think, would really benefit from reading the book beforehand. But it's there as a guide to tell you what to do. But I don't mandate that you read it beforehand. Right? Question?
Does practice exam get graded, or will solutions be posted before?
I'll post the solutions. I won't grade it. It's just for your own knowledge, like, oh, I only got through half of the exam in the 15 minutes. Maybe I need to brush up on some things. So it's there as a guide for all of you. Okay, any other questions? All right, so this is the whole semester laid out. The videos get a little bit thinner towards the end, partly because when I made all those videos, I ran out of steam, partly because the amount of concepts, the fundamental concepts, become thinner, and then the challenge becomes the complexity of tying it all together, right? So a lot more computational tools and things like that. All right, so then, so the links on the YouTube, so these will be provided to you on the Canvas page, but I can't show you the Canvas page. This is last year's playlist, right? With the same classroom and everything like that. And then this is the playlist for this year, which is empty right now because this is our first lecture. Okay, so I think that covers all that I wanted to on the logistics. Oh, one last thing on the logistics. Everything's going to be graded electronically. So PDF, scan your homework, upload it to Canvas, as opposed to handing it back. And that's just a convenience because when I last did paper exams or paper homeworks, every week I have to pass it out individually to like 50 people. It's a big time commitment. So it's just easier to do it all electronically. So if you don't know, I don't know, I'm sure Android phones have this, but on Apple, on iPhones, you can use the Notes app to scan documents, right? So if you open up your notes and you go to, I think, plus or like insert, there's an option that says scan documents. And then you can go scan, change the page, scan, change the page, scan, change the page, scan, change the page, right? Don't take pictures because that makes it really, really weird because then sometimes you open it up on Canvas and it's like this big of a document. Okay, any other questions about the logistics before we move on to the more fun part of the class or less fun part of the class? Was that?
The what part of the class?
The more fun part of the class. Okay. Okay, so fundamentals of process engineering is oftentimes referred to as mass and energy balances because the exact name doesn't matter, but the content is universal across chemical engineering. So what makes this class somewhat unique from what you've previously taken is that I think it's the first sort of real engineering class. And what I mean by that is it's not a math class, it's not a science class, it's an engineering class. Right? So that's why my recommendation is to get a calculator that does the math for you. So the unique and challenging part of this class is not how difficult the math is. It's not how difficult the chemistry is. It's not even how difficult the thermodynamics is. Every single component of this class you have already seen before. The most advanced math that we're going to do is systems of linear and systems of nonlinear equations. Who is comfortable with Python?
Define comfortable.
Can you solve a system of nonlinear equations in Python?
How do people do that? How is anyone here able to do that? I don't get that.
Solve systems of equations?
In Python.
Oh, fsolve. Have you used fsolve before? Okay, what about Excel Solver? Who's used Excel Solver before? Okay, do you guys know how to solve systems of equations with Excel Solver? Okay, so we'll go over a few strategies for computer programming. Okay, but you've all taken ordinary differential equations and linear algebra, correct? I believe it's a prerequisite for this class. Okay, who remembers reduced row echelon form? Perfect, that's all I remember from that class also. The math required, you are better at math than this class requires. Okay? You are better at chemistry than this class requires. Thermodynamics, if you did really well in your thermal class, you might be better, but we'll teach you a little bit more thermodynamics. But the challenge of this class is it's the first class, I think, for many people, where I expect you to actually remember your previous courses. Okay? I'm not going to cover chemistry. I'm not going to cover math. We're going to derive a system of equations, and I'm going to say, look, process engineering, done. Job solved. Now it's all up to you to recall how to solve that system of linear equations. We'll do a little help sessions, right? But for the most part, the biggest challenge of the class is you're expected to remember and to apply the previous coursework, right? So many times this class is kind of like just sort of an advanced puzzle that we're trying to solve. Right? So we're going to build some sort of a complicated chemical process. So for example, the most common one that we're going to see here is a reactor separator. So this is we have a feed coming in. It gets mixed with a recycle stream. Recycle. We have a mixing unit. We have a reactor. We have a purge stream. We'll talk more about this when we get into the details. You basically need a purge stream to get rid of inert and non-reactive components. And then we have a product that we're trying to sell. Now, our goal in process engineering is to design these unit operations. So the reactor obviously involves some extent of chemistry. So I'm not going to go over the chemistry. We're just going to present the equations as if they're true. And hey, this is a reaction that occurs. Don't worry about it, right? Our goal as chemical engineers, and more generally as living, breathing human beings, is we take in simple, small, cheap chemicals. So in the case of humans, that may be sugar, nitrogen, oxygen, and we turn them into big, complicated, expensive molecules. Proteins, cells, organs, right? As chemical engineers, we do the same thing. So we may take in methane and water, and we may spit out methanol, right? So we buy cheap, readily accessible materials, and we convert them into expensive, valuable, hard-to-manufacture materials. The cheaper, the more efficient that you can do this process, the more energy you save, the better it is for the environment, and the more money you make for your employer. Right? So the traditional chemical engineering approach, and one that we're going to kind of follow here because it's an introductory class, is on traditional petrochemicals. Right? So this is your classic refinery, this is your classic chemical plant. That when you see and you take a random person off the street, they'll look at a refinery, they'll look at a chemical plant, and they'll say, oh my God, look at that gross, disgusting, polluting, terrible piece of industrial machinery. But I always have a different take. I view a chemical plant as the single most efficient apparatus or device that basically humankind has ever assembled and put together. Because when we're buying our chemicals, we're buying millions of tons of it a year. And so even the smallest percentage increase in efficiency is enough to save millions and millions of dollars. Right? So that chemical plant, yes, it does use a lot of energy, but it saves way, way, way more energy than if we were to do it individually on our own. Right? It is a very highly optimized piece of equipment. So the examples that I like to give are one, back, maybe 10, 15 years ago, is biodiesel still a craze? I think it's kind of fallen out of fashion. But I remember when people were like, oh, you can make diesel from used vegetable oil. And they would be doing it in their garage. And they would be using really harsh chemicals, like sodium methoxide, which is a really strong oxidizing agent. And I would just think, wow, that is incredibly inefficient. And yes, you're using your vegetable oil, but in the process, you're probably causing more harm than good if you're doing this in your garage. Right? Much better to do this on an industrial scale with advanced engineering controls. The other example is, let's take your car. So when you have a car and it's cold, like on January, and you start it, your gas in your tank is at the ambient conditions of the air. Your engine is going to be heating up to several hundred degrees. So that means that you're losing efficiency by taking your fuel at 20 degrees Fahrenheit, heating it up to the engine temperature. That is inefficiency that you're losing in the process. So how could we make our engine run more efficiently? Well, we could take the exhaust gas stream and we could use that energy to preheat the gasoline. That way your gasoline, when it enters the engine, is at the engine temperature. Now, why is that a bad idea for cars?
Gasoline is extremely flammable.
It is, and how well do people maintain their cars?
They don't.
Exactly. That's why they don't do it. But in a chemical plant, you bet your bottom dollar that they are going to do that in every possible opportunity that they can to squeeze out as much energy efficiency as possible. Yes?
They also just never turn off for the car, other way to make sure that the engine's running at peak efficiency, so never turn it off.
Exactly. Chemical plants, refineries operate 24/7. The goal is that they operate at exactly the same condition for their entire operation. They only shut it down when they need to. So at a refinery, it's called the turnover, and they might have a turnover once every 6 months or once a year. That's usually to replace catalysts, upgrade equipment, and make repairs. Why do we run these at exactly the same condition 24/7?
Efficiency.
Why is it efficient that way?
Because if you find the most efficient conditions, you just run it at those conditions forever.
Exactly. So we, chemical engineers, spend a lot of time modeling this and figuring out, hey, if this reactor is run at 20 megapascals and 500 degrees C, if this separator is run at 10 atmospheres and 60 degrees C, right? Then I can get this whole process to only consume X number of gigajoules of energy. And that's the best that we came up with. that's where we're going to operate it as. As a young process engineer taking on your first job, you might realize, hey, if we changed out the catalyst for this, we could now run this instead of at 500 C at 450 degrees C. As it turns out, that may save more energy than an entire small city's worth of energy. And guess what? It could save the company $20 million a year. Right? These are real cost savings of what we're doing as chemical engineers. So, chemical engineering is often criticized due to its lack of hands-on nature. Right? Have you guys ever heard this at all? Chemical engineering is often called a virtual engineering. Right? Mechanical engineers, they always get to make those egg launchers where you build a little robot and it launches an egg. Electrical engineers get to play with little breadboards. Right? So the Department of Chemical Engineering has put a lot of time and effort into developing 1703 and 1705. So you guys get to do some hands-on stuff. Me personally, I like chemical engineering because it's a virtual engineering. I don't particularly love building egg launchers or playing with breadboards. I like the fact that we can do all of our work basically on a computer. Right? And that's why I think chemical engineers get paid a lot more than a lot of those other engineerings. If you can tolerate and stomach the fact that you're doing all of your work on a computer, that you don't actually probably will ever turn a wrench in your lifetime, right? If you can tolerate that, handle the chemistry, handle the physics, handle the math, handle the programming, that's why we get paid the most of any other engineering discipline. Yes, question? That may be a challenge. Now, there are chemical engineering disciplines we probably don't sit in front of a computer, but I don't think there's many jobs that exist nowadays that don't involve a lot of sitting in front of a computer.
Well, I don't want to just sit in front of a computer.
There's a lot of career options. There's a lot of career options.
I chose wrong.
We can chat later on. Okay, so the objective of this class is mass and energy balances. Okay, so we need to figure out how much mass we're putting in of what composition. We need to basically make sure we don't make any mistakes. Right? The whole purpose of this class is don't make a mistake. Right? We have basically two laws that we're going to follow. Law of conservation of energy and law of conservation of mass. Don't make a mistake. Don't lose track of any mass. Don't lose track of any energy. Now, so we're going to feed material of a particular composition at a particular flow rate. We're going to remove material of a particular composition at a particular flow rate out of two streams. There's a lot of complexity that goes on in between here, but at the start, we don't have to worry about that. We just look at the big picture. How much mass is in, how much mass is out. Same thing with energy. How much energy are we putting in, how much energy are we taking out? Then we also have to concern ourselves with the reactors. Right? How much energy is being generated or how much energy needs to get put into this reactor if it's endothermic versus exothermic? What is the equilibrium constant of this reaction? Right? So how do I solve for the chemical equilibrium of this using Kas and all those different things that we've done? Separator involves a lot of thermodynamics. If I operate this separator at a given temperature and a given pressure, how many phases are going to form and what are the composition of those two phases? Right? So the whole objective of all of this is to simplify how many variables that we are going to control. So we basically can only control the temperature, pressure, and flow rates of everything coming in and out of these streams. And from there, we want to be able to generate a product that is 90% pure with 90% efficiency from the feed reagents. Right? So all the work that we're going to do may seem hopelessly convoluted, but the objective is to essentially reduce the number of variables that we can control to figure out which ones that we want to manipulate in order to get a particular outcome. All right? So let's go over some engineering basics. Oh, one last thing, teaching style, chalkboard. I'm all chalkboard. Because there have been studies, so if you type on your computer, you can transcribe more words. But your conceptual comprehension is lower. So if the content that you're trying to learn is all focused on terminology or rote recollection, then a laptop may be the more efficient study means. But if the challenge is in concepts it's been shown that if you write down the notes and you get fewer words, right? But the process of writing it down sort of triggers more regions of your brain. It forces you to translate what is being spoken to what you're writing down because you write slower than you type, right? So that process all sort of imprints upon your memory sort of a little bit of a history of what was going on in the class when you wrote it down. So I'm always a chalkboard type person. Okay, one question to start off. How many hours will you have to work as a chemical engineering graduate to pay for all of your textbooks? Well, so don't answer right now. There's no right answer. Take a moment and think through this sort of problem and give me a way that you estimate this, okay? How many hours do you have to work in order for you to pay for all of your textbooks? So hold on, take a moment, and then I'll call for volunteers later. But
You mean work like after we graduate?
after you graduate. So that may necessitate, okay, how much do you make per year? How much do you make per hour, right? And how many hours do you have to work to pay off all of your textbooks? And then I'm going to show you the difference of starting salaries. This is $2015, so who knows what it is in $23. I haven't done that inflation-adjusted calculation just yet. Okay, how many hours do you have to work? Someone want to volunteer?
None, because I pirate them all.
All right, that's one answer. Okay.
30 hours.
30 hours? Okay. How'd you come up with that number?
Average how much I spend per semester, times that by how many semesters I go, and then calculate the average salary of the starting graduate, and then divide that by 54 weeks a year, and 5 days a week.
Okay. So you said 30 hours, so about 1 week. Anyone else? Tell me what numbers. Did anyone actually do the exercise? Yeah, here we go.
I did. I got about like 22 hours.
Okay. So what do we think that the salary difference is between getting an A, right? So it's in $2015, chemical engineer starting salary according to the C&EN, Chemical and Engineering News, is $72,600. Okay? A minus, $67,200. B, $62,000. Well, $600, I'll round it.
Wait, what are these letters representing? Are these like
This is your starting salary.
for different GPAs?
Yep. And if you get a C average, 44,800. Okay, so is it worth our time to complain about 30 hours, so about 1 week of 1 year of a 50-year career, to get a little bit better of a GPA? Which is the better exchange? Don't buy textbooks, don't buy resources, don't buy a TI-89, right? And save yourself $500 or $5,000 more your first year, right? Use all the tools at your disposal. You are investing in yourself right now, right? You're investing in yourself. It is best for you to use as much resources as you can to get as best grades as you can, because that will give you the most opportunity. All right, unit conversions. Who feels comfortable with unit conversions? Everyone does. Okay, so I don't have to go over that. Skip that one there. Scientific notation. Okay, sir.
Are you comfortable or if we want to hear?
Are you comfortable? Comfortable with scientific notation? Okay, good. Significant figures, we good on that one?
Sorry, what was the first thing?
First one was unit conversions. Centimeters to inches. Feel good on that one? Okay. Scientific notation, giga, mega, milli. Feel pretty good? Okay. Significant figures, right? You take the leftmost or the rightmost digit when you add them. Okay, here we go on that one. Okay. Dimensional homogeneity. How do you feel about that one?
Oh yeah, no, I know.
Okay, this is probably one of the best concepts that engineers know and use to their advantage. Dimensional geneity. Now, you've probably seen this concept. Maybe you haven't heard the term before. Okay. So if I have units, okay, if I times or divide them, anything goes. Okay? So if I have feet times by pounds, that gives me foot-pounds, right? If I have newtons and I times them by meters, I get newton meters. Make sense? If I add or divide, what is the rule that I have to follow?
If you're adding and dividing different units?
Correct. If I'm adding and subtracting two numbers, yes, back here. They need to be the same. Can I add centimeters to inches? No, I can't. So, same units. Now, if I have on the left-hand side and the right-hand side of an equation, what rule must I follow? Yes, same units. All right, now we think, yeah, we're all experts on this, right? Okay, I've got a problem for you. I have an equation here. D equals 3t plus 4, where I specify that t must be in units of minutes. Okay? D is measured in feet. What are the units of 3 and 4? Yes?
4 is feet and 3 is feet per minute.
Okay, so this one has to be feet, and this one has to be feet per minute. Okay. Okay, now what I want you to do is on your own, I want you to rewrite this equation, but instead, I want D to be in centimeters, and I want T to be in seconds. So rewrite this equation for me.
But like have the same.
Same exact formula, just changing the units. Okay? So now I don't put T in units of minutes, I put T in units of seconds, and I want D to tell me how far in centimeters. Okay, who's got the numbers? We got it worked out. We got 1, 2 people. Okay, I keep working for a little bit. We've got about minus 15 seconds till the end of class.
Sorry, are we converting or rewriting?
Rewrite the equation such that I can input time in seconds and get D in centimeters following this 3t plus 4 that was originally in feet and minutes. Do you get the numbers?
Yeah. D times 30.48 equals 30.48 over 60 times 3t plus 4 times 30.48.
Okay. In terms, can you type those numbers out, like give me an actual like equation? Yeah, what do you got?
1.5t plus 120.
Very close. I think he rounded off some sig figs on there, but yes, that's right. Okay, so let me show you how we do this, right? So this is going back to our unit conversions. So let's start off with 4, right? I want this, it's in feet right now. I want this to be in centimeters, right? Because this has to be in centimeters, this has to be in centimeters. So I write blank centimeters is equal to 4 feet. 1 foot is 12 inches. 1 inch is 2.54 centimeters, and that will give me 122. This one here is right now in feet per minute. I need to get this into centimeters per second to get my dimensional homogeneity to work out. Blank centimeters per second equals 3 feet per minute. So we do the same thing here. 1 foot, 12 inches. 1 inch is 2.54 centimeters. And then we have 1 minute is 60 seconds. And that gives me 1.52. So then I can rewrite my equation. D is equal to 1.52t plus 122. All right. So this is going to be indicative of the types of problems that we're going to be working on. The concepts are going to be relatively straightforward. Don't lose mass. Don't lose energy. Follow the first law of thermodynamics. Those are the rules that we're setting forth for the class. But we can do very complicated systems with very simple rules. Okay? All right. See you all on Wednesday, and welcome back to the semester.